Hello, my name is Nathan Sheely, and this is my presentation of my operating system for CSCI E-92 Spring 2024. Now, I started off naming my operating system Ouroboros, which came kind of long, so I shortened it to OB, since it's an operating system that became OBOS, and I wanted the big final feature for it to be audio playing, so that became DJOBOS, or as I like to call it, JOBOS. Now, the main interface for talking to JOBOS is a shell in a terminal emulator over UART. I have a help dialog, which presents a bunch of the functions that JOBOS can perform. The shell supports several things like double-quoted strings for arguments that have spaces in them. I have escape characters, so I can have a -T for a tab inside of a shell entry, as well as double quoted or to have quotes inside of it. I also have my own memory allocator with malloc and free, and I have a memory map which you can print off every block of memory that's been allocated. And I also added a bunch of debug flags for different configurations, and probably my favorite one is the debug memory flag, where the memory map also adds the file name, line number, and function name of every block of memory of where the malloc call was that block was allocated. JOBOS also has a device-independent I/O layer, so it supports all these devices, LEDs, push buttons, and whatnot, and it has this common interface for all of them that's POSIX-like, so I can call fopen and open any of these devices, and then I can read, write, put whatever, and then close it, and all these will interact the same through this interface. There's some limitations, like you can't really write to a potentiometer, but you can read from it. The biggest device is, well, one of the really big devices is probably the FAT32 on microSD. As you can see here, I mounted the device, I listed the contents of the root directory, and I support files and folders, creating, deleting, reading, writing, all that. When I list the output, I can have full output, which includes by default the last modified date time, the size of the file, any attributes like if it's directory or archived. I have different flags if you want to get the creation or access date. I also support date time and keeping track of that with a flex timer that triggers every millisecond in order to increment it. You can also set the date time with a ISO 2601 date time stamp, and once we do that, we can then create a file and it'll have that timestamp or the current timestamp. And also the directory it's in, because we've changed the contents of the directory, will be updated for the new last modified date to match that. Its child directories, all the ... entries in there will be updated, and in its parent directory, the named directory entry for it there will be updated all to have the new last modified date. Now, JOBOS also has multiprocessing, so we'll see here in a second. I'm running a multitask command that actually launches 3 processes. One, it gives the name of a file, and any terminal input will be copied to the file. If I hit the push button, it'll output to the UART what the push button was pressed. I also have a process running in a programmable delay block, blinking the orange LED off and on. When I hit Control D, it closes the writing, which then allows the main process to kill off the process with pulling the push button, and then I actually awaken the process for the programmable delay block so it can unset it and clean itself up, and then we all return and I can print off the message. This is a test of multitask that I wrote. Now, next with multitasking, I'm going to change the directory up I'm going to show off printing off a large file. I'm going to spawn a process called touch2LED, which pulls the capacitive pads on the top of the board and lights up the corresponding LED as they're being touched. So I've started both processes, and they've used about 1,000 milliseconds of CPU time as it schedules between them. And now I'm going to print off the Alice in Wonderland by Lewis Carroll, reading from the SD card, printing out over UART to the shell, and while it's printing out, I'm messing around and showing that I have a good response time still on the touch to LED. So touch the pads, the LEDs light up. It's all pretty instantly and without interruption. And here I'm going to show the commands, and since they've been running, they use more CPU time. And they're about 10,000, 20,000 now. I've also implemented support for the LCD, the display, and I have a bitmaps folder, so with a bunch of bitmap images, and I supported writing those images to the display. So here on the left you can see a bunch of header data about the image, and on the right I printed the Windows XP Classic Rolling Hills background out to the display. Next I'm going to write a Mario image, which you're going to see is going to take a few seconds. And then after that I'm going to write a Mega Man image that is actually run length encoded, and you can see it happens almost instantly, but it's about the same size as that Mario image, which is kind of cool. It shows the bottleneck is actually reading the data off the disk, not displaying it to the screen. With that, we're going to move on to the big presentation, the audio, which I decided to implement, which had me feel like JOBOS is more of a, like Job here, Will Arnett's character from Arrested Development. Audio is tricky. Okay, so in order to implement audio, there's a bunch of stuff we're going to have to do. We're going to have to figure out this whole tower audio SGTL board, which I'm using connected to the main board over the tower in order to produce the audio. It uses an SGTL 5000 codec. It's the little chip that handles all this. I have to configure it with I2C. I have to send it data over I2S. I'm going to find that I really need to use DMA in order to handle sending this data, or else it's not going to work well with a multiprocessing system. I'm going to generate some waveforms to send over from the I2S. And before we get started, the type of data we're sending is pulse code modulation, which roughly translates this analog signal to points of amplitude over time. You can think of it as like the position of the cone inside the speaker. And as that changes, it's back and forth produces the sound you hear. Now, first off, we have I2C. It's a 2-wire protocol. A bunch of old documentation you'll find uses the terms master and slave. I found the more modern terminology is controller target. So we're going to set up the K70 as the controller, and everything else that I talk to as a target. It's essentially the controller does everything. It initiates communication. It starts off with the address of the device it wants to talk to. So it turns the wire on, says what device it is. It's going to then say what register on the device, if necessary, which it is here, I want to read or write from. Each bit will have a read or write bit saying, hey, this is what I'm going to do. And if we're reading, it's however many bits we'll read off, or if we're writing, however many, it keeps repeating, writing it off. And every 8-bit word that it sends is followed by an acknowledgement by the target that, yes, this succeeded. With that, I found there's an accelerometer on the K70 board, so I can actually test the I2C before getting further. So I'm reading off data from the accelerometer, and I'm going to move Job around, and you're going to see the values change up and down, positive, negative, as I change orientation, and the way gravity is pointing down on the accelerometer, the values will change. Come on. All right, next, since we got I2C working, we have I2S. I2S is another protocol with its own bus. It has 3 clock lines. All of these have different words to refer to the same thing, so it gets a little confusing. First, we get this bit clock line, which sends a single pulse per bit that comes across. Then we have our word clock line, which is, its period is the word size of the audio samples we're sending across. Then we have the data line, which is the actual audio data we're sending. All this is extremely timing sensitive. So our bit clock line needs to be a multiple of the product of our sample rate times our bit depth, which is the number of bits per sample, times the number of channels we're using, in this case 2 for stereo audio. So the clock we use needs to be a multiple of 1.536 megahertz for this to work. So we figured this all out. Now to configure the actual board, first off, we need to just send a whole bunch of I2C messages in order to set this all up. We got to power up the system. We got our linear voltage reference regulator. We got our DAC. We got any amps, everything we power up. We need to tell it what our sampling rate is going to be. 48 kilohertz is actually chosen because it is above the frequency following the Nyquist sampling theorem that you can perfectly recreate any audio a human can hear, and it's easy to set up with the clock we have. And then we have a sample depth of 16 bits in stereo audio. This is all roughly the same as a CD-ROM, except that'll be 44.1 kilohertz. But in order to do that, I needed some phase lock loop configuration that I just didn't want to deal with. 48 is easier. We're using the clock off of the audio board that is provided. So with all this configuration, it's an I2C target, is the I2S clock controller, and is the I2S data receiver. The controller and target over I2S are entirely independent of who the receiver and the target is. You can read the specifications, like 14 pages. It makes that very clear. Now, in order to get the seamless audio without underbuffering or anything like that to work well, I found you really need DMA setup. So a direct memory access system where it's reading off a buffer of memory where you put the audio and writing it out to the I2S bus. So what's common with these timing sensitive applications is to have multiple buffers. In this case, double buffering. 2 buffers are called a ping pong buffer, where the DMA will write from one buffer while the CPU writes to the other. And when the DMA reaches the next one, it'll send an error up to the CPU and tell it, hey, I switched, go to the other one. So the CPU changes which buffer it's writing to. And when it finishes, they'll just loop around and they'll ping pong back and forth which one's reading and which one's writing. And with that, we can demonstrate the audio we have. I create a function where I can specify the wave type and the frequency. Here is a sine wave. It is, in terms of audio, the simplest wave, or any signal, the simplest you can have. Next is a square wave. It has that same main frequency, but you have some harmonics added in. Now a triangle wave, which is very similar to square, but the harmonics are a little less pronounced. And finally a sawtooth wave, which is a little bit more of a buzzier sound. And next I try a frequency that's too low to be caught on this microphone, even though it's there. And then finally I leave off with a flat line, which is no sound at all because you're not changing your amplitude at all, which is super helpful for debugging because if you hear sound or noises, it helps you figure out what's wrong. Thank you. I hope you enjoyed this presentation.